In this video, we're going to look at trigonometric integrals, so integrals with trig functions. We've already done a couple of these where we applied basic properties or identities to, but I just want to go a little bit more in depth and show a few other tricks that we can use with these. So the first thing that we're going to look at are powers, products of powers with sine and cosine. So these would be things where we see an integral of sine times cosine, but those things are being raised to powers. So we're going to look at three different cases, or three more interesting cases. If m is odd, meaning that the sine function is odd, then we can take the m and write it as what an odd number looks like, 2k plus 1. Any odd number is an even number, which is 2 times any number is even, and adding 1 guarantees us an odd number. So then when we write that m as 2k plus 1, we're going to use sine squared equals 1 minus cosine squared to get sine m of x equals sine to the 2k plus 1, just replacing the m of x. And then what we can do is we can break up that exponent. We know that if we have multiplication of like bases, we add their exponents. And if we have an exponent to an exponent, we can think of that as multiplication. So the sine of 2k, we can write as sine squared to the k power. And then the plus 1, we can break that off as its own sign. And the advantage to doing this is anytime we have that sine squared, we can write that as a 1 minus cosine squared. And that's going to be handy because that's going to allow us to use some u substitution. But notice we're working everything into those cosines except for the sine, which we're going to take care of using when we get to the u substitution. So we'll see how that works. Next, if we think the n is odd, the number on the cosine is odd, exactly the same process. We're going to take that n, we're going to write it as an odd number, so 2k plus 1. We're going to replace that cosine squared with the Pythagorean identity 1 minus sine squared. And then we can express the cosine mx as cosine 2k plus 1x, which we can break up as the cosine squared to the k power times cosine of x, which then we replace cosine squared with the 1 minus sine squared. And then finally, case 3, if m and n are both even, we can substitute the power reducing formulas in for those. Sine squared of x is equal to 1 minus cosine 2x over 2, and then cosine squared x is equal to 1 plus cosine 2x over 2. So we're going to see examples of all these. Now you might be saying, well, what if both of them are odd? Well, then we can use kind of case 1 or case 2 with some u substitution. But if we have one or the other, that's where case 1 or case 2 apply. So let's do, as our first example, let's take the integral of sine cubed x cosine to the 4th x dx. So the first thing I'm going to do is consider which case I have here. And so I see that the 3, that is my odd power, that is on the sine. So that's equivalent to case 1 if the m is odd. So I'm going to immediately take this and I'm going to write the sine, write as sine squared x times sine x, cosine 4x. I'm really just going to break this down. I'm going to break it down to single lines. I'm not going to try and just jump from here to here all inside my integral. So I've just pulled off one of those signs. So then I have this even power here that I can write this as a 1 minus cosine squared. And here we only have a sine squared, so there's no exponent around that, right? We don't have an exponent here because it was just a sine squared times sine. We still have our dx here. So again, what was the purpose of all of this? Well, now what we're going to do is we're going to use a little u substitution. We're going to let u equal the cosine of x. And so that means our du is equal to a negative sine dx. And so we can think of dx as du over a negative sine. And how does this help us? Well, let's see. So we have the integral of 1 minus u squared. We have that sine x there. We have cosine to the 4th is just really u to the 4th. But then dx, we've just replaced that with du over a negative sine x. And so we see those sine x's cancel. We can pull the negative to the front. We have the integral of 1 minus u squared times u to the 4th du. And now we can multiply this out, get a very nice polynomial here. And I can take the antiderivative of each of these very easily. So the antiderivative of u to the 4th is u to the 5th over 5. And then if I distribute that negative as I go, we'll have u to the 7th over 7. And then, of course, because we are dealing with an indefinite integral, we have our plus c. And so now we would need to go back and replace those u's with what they should be, which was a cosine of x. So cosine to the 5th x over 5 plus cosine to the 7th x over 7 plus c. And that was pretty easy once we made that substitution. The trick was just recognizing that we need to make that substitution. Or replacing, really breaking apart that sign. So the goal is to get to those even powers, because when we have those even powers, we can replace them very easily with the other trig function. And then the one that's left over, we can cancel that out. And so we can see how if this had been sine to the 3rd, cosine to the 5th, we could have used the exact same logic. We just have a cosine 5th here, which is hanging out as u to the 5th. So if both of them are odd, then we can just think of using case 1 or case 2. It doesn't matter. Let's do another example. Let's take the integral of sine squared x cosine to the 7th x dx. So now it's the cosine that is the odd power, so that's the one that we want to break off apart. We also see that this cosine is much higher than just a cosine squared times cosine, kind of like what we saw in the first example. So I want to write this as a even power, which means I'm going to have to pull off that single cosine. And I also want to take this cosine and write it as a cosine squared, which means I'm going to have to raise that to the 3rd power. And I forgot an x there. Okay, so the next thing we need to do is we need to replace that cosine squared with sine, because remember our goal is to have pretty much all the one trig function, except for that cosine hanging out back here is fine, because that's what we're going to use to get rid of the u substitution, the dx, when we do our u substitution. That is our next step. So let's go ahead and let u equal the sine x, which means that du is equal to cosine x dx. So now everything's going to replace really nicely. Sine squared would be a u squared. 1 minus sine squared would be 1 minus u squared, but then we have that cube power there. And then notice the cosine x dx is the new du. So if we wanted to, we could have solved this for dx and then made that replacement in our equation. We could have done that. That would have been fine. But it does work out a little bit more cleanly this time. It's just direct replacement. So we do need to take this 1 minus u squared and cube it. So if you remember your Pascal's triangle, it makes it a lot faster. I'm going to work this first one out just kind of the slow way, multiplying it out. So if we took 1 minus u squared and squared it, we'd have 1 minus 2u squared plus u to the 4th. And then we're going to multiply that by another 1 minus u squared du. So we have the integral of u squared. So we'd have 1 times 1, which is 1. 1 times the negative u squared is negative u squared. Negative 2u squared times the 1 is negative 2u squared. I lost where I was. Let's see, we have our 1 times 1, 1 times u squared. So we have our negative 2u squared times a negative u squared is a plus 2u to the 4th, plus another u to the 4th, and then we'll have a minus u to the 6th. And then to clean this up, just collect our like terms. We're still going to have to distribute that u squared in front, but we'll have a 1 minus u squared plus 3u to the 4th minus u to the 6th. So we see that Pascal's triangle there. The 1, 3, 3, 1 with the coefficient being the negative 1, so that's switching our signs a little bit as we go through there. And then, like I said, finally we're going to distribute that u squared, so u squared minus 3u to the 4th plus 3u to the 6th minus u to the 8th du. So it's not that it's a one-step problem, but this is now solvable, right, by switching to our signs first off and then making that u substitution. Right, so now we can take the antiderivative of this. We'll have u to the 3rd over 3 minus 3u to the 5th over 5 plus 3u to the 7th over 7 minus u to the 9th over 9 plus our c. And then lastly, we just need to go back and replace the u with the sign. And that will finish off this problem. And so we've looked at now the first case. Should be x's, not u's. We've looked at the first and the second case. We haven't looked at the case where they are both even, so we'll do that next. Of course, I've gone very much just straight through the cases, and the challenge when you're doing these problems on your own is to recognize which case you're dealing with, and also should we even be using this. But anytime that we see these trig functions with powers being multiplied, that is a good indication that this is going to be a useful trick. So then let's take our third example. we're going to take the integral of sine squared x cosine squared x dx. And so anytime we have those even powers on both trig functions, what we really need to be using are our power reducing formulas. And so the power reducing formula for sine is 1 minus cosine 2 x over 2. And then for the cosine, looks pretty much the same, but with the plus in between, over dx. And so now we can, for one, multiply those 2's together in the denominator, factor that out, I'd say 1/4. That'll make our lives a little bit easier. And then the other thing I can do is FOIL or multiply those two, 1 minus cosine, 1 plus cosines together. So we'll have one, well, the positive and the negative will cancel, so that works out nicely, and we'll be left with a minus cosine squared of 2x dx. And so the 1 very easily is taken care of, right? We can find that antiderivative right away. But the cosine squared, we have to apply another power reducing formula to that. So we'll have minus 1 plus cosine. Our initial angle is 2x, so we need to double that. It's going to be a 4x over 2 dx. And so now everything here we can find the integral for. We can find the antiderivative. 1/4 is going to be in front of everything. Antiderivative of x is of 1 is x. Then we have a minus 1/2. That'll be a minus 1/2 x. I could have actually simplified those two things first. That would have been a little bit easier, but it doesn't matter. And then we'll have a minus. The antiderivative cosine is sine 4x. Of course, it was over 2, but then it also has to be over the 4 because of that chain rule. If we're to take the derivative of sine 4x, we would have cosine 4x, and then we'd have to multiply by the inner derivative of 4, and so we need that 2 times 4. Then, of course, we need a plus c there. Just to clean up a little bit, x minus 1/2 is 1/2 x, and then minus sine 4x over 8 plus c. Now you might be questioning why it's plus c on the outside. Remember, it doesn't matter. It is that arbitrary constant. The c is just whatever we would have to solve for in our next step for the initial conditions. So if we were to have it on the inside, it would just be, whatever value you'd find would be 4 times larger than it's on the outside, or vice versa. All right, so let us move on to the next skill that we're going to be able to work on, and that is eliminating square roots. Eliminating square roots. We're just going to jump right into an example on this one to see how this works. So let's integrate from 0 to pi over 3. I'm just giving us a definite integral this time just to vary it a little bit. It doesn't matter if it's definite or indefinite. We can do the same things. But 1 minus cosine of 6x dx. So if we have a square root with a trig function, that is much easier to handle than without a trig function, actually, because of the things that we used before, those power reducing formulas. So what I'm going to use here is I'm going to use the power reducing formula for when I see the 1 minus cosine power reducing formula, and that is for sine. So let me just write that down again so we can see it off to the side and we can compare. Over 2, sorry, getting ahead of myself. So this is our power reducing formula over here on the right. Now what we see is a 1 minus cosine 6x. So I could very easily replace the 2x here with a 6x by multiplying this by 3. And so maybe, maybe I shouldn't have called this x, maybe I should have called it theta, maybe that'll help. So what we're doing here is we're saying let theta represent 3x. And so that's going to get us closer to what this looks like. But notice we still have just a 1 minus cosine 6x, not the over 2. Well, I can just move that over to the other side as well. This is just an equation, so it all has to be able to move around. We have to be able to manipulate it. And so now we have a nice simple replacement for that 1 minus cosine of 6x. So we can write this as the integral from 0 to pi over 3 of the square root of 2 sine squared of 3x dx. Now why has this helped us? Well, we have a perfect square on the inside of that square root. That is what we're doing here. We're using the power reducing formulas when we have that 1 minus cosine or 1 plus cosine format to turn it into a perfect square root. Now, is this always going to work? No. If we had 3 minus 5 cosine of 6x, that's not the power reducing formula, but because of the way it was situated, we were able to use that power reducing formula in a way to replace it so we had a perfect square. So now we can write this as 0 to pi over 3. We have our root 2. The root 2 is still on the inside. The square root of sine squared is just sine of 3x dx. And really, it's the absolute value of it, because the sine squared had to be positive. Therefore, if we take its square root, it has to be positive. So we do need to include those absolute values there. Now, if we were to take the antiderivative of this, we're going to have the square root. If we're looking at the integral that we're working with, we're going from 0 to pi over 3, that's strictly going to be positive for sine. So we don't need to worry about that absolute value. We can just take its antiderivative, which is a cosine 3x, and it should be a negative. We'd have to have that over 3 as well, because we do have that inner function of 3x. We'd have to take the derivative of. Of course, we're evaluating this from 0 to pi over 3. So now we're just going to plug in, and I might go and pull that 3 to the front as well, just to make it easier for myself. So I'll have cosine of 3 times pi over 3 minus cosine of 3 times 0. And we're going to get negative root 2 over 3. Cosine of 3 times pi over 3 is just pi, so that's going to be a negative 1. And then cosine of 0 is a 1, so we have negative 1 minus 1, which is, of course, negative 2. And negative 2 times the negative 2 root 2 is 2 root 2 over 3. And there's our answer. All right, let's look at one last type of thing that we can do with trig functions, which is the product of sines and cosines. So, again, not to say that this is all the skills we can possibly apply to sines and cosines or the integrals thereof, but just 3 of the things I'm going to show you in this video. So if we have a product of trig functions, sine times cosine, cosine times cosine, we can apply our product to some formulas. And the advantage to this is if we have the integral of a product, we don't know how to find that, but we can take the integral of a sum or a difference. And so that is what we're going to do here. So let's take an example. Let's take the integral of sine 5x cosine 3x dx. Now, if you guys remember back to trig, you may have learned these as 4 different product of sines and cosines. Notice I'm missing the cosine times sine, but multiplication is commutative, so we can just rearrange that if we want to. We don't need 4 unique cases. 3 are sufficient. So if you do have the cosine times sine, just flip it around. It doesn't matter. So if I were to take this integral, I wouldn't know how to calculate it. Let us then apply the product sum formula. And so it is this middle case. So we're going to have the 1/2 sine of, we have to subtract the 5x minus the 3x. I'll write this first one out in all its detail, or could just say 5 minus 3x. And then we'll have plus sine 5x plus 3x dx. And so I can pull that 1/2 to the front of my integral. 5 minus 3 is 2x, and then 5 plus 3 is 8x. And so now we can integrate this very easily. The antiderivative of sine is a negative cosine, and that had to have been divided by 2 because we'd have to apply a chain rule, have to apply that inner derivative. Then we'd have a minus cosine 8x over 8, and then we need our plus c. We can do a little bit of cleanup if we want to. We can distribute that 1/2. So we get negative cosine 2x over 4 minus cosine 8x over 16 plus c. That's all there is to it. So I'm not going to do any more examples of this rule because it is just a simple matter of, if you see that product, we can write it using our product sum formulas. So we do need to remember some formulas from trig. In these sections, we need to know how to work with trig functions. We've already talked about some of the basic identities, the Pythagoreans, the quotients, or reciprocals. But we need to know the product sum. We need to know our power reducing. We are going to be applying half angles as well at times, and we need to be comfortable using those to eliminate the square roots as well. Now, we've only talked about sines and cosines in this video. What if we have tangents and cotangents? Well, there are a lot of rules that apply to those as well, so I'm not going to go into those in this video, but for starters, we could just convert them over to sines and cosines. That is always can be a useful trick. But then on top of that, we know how to apply Pythagoreans to those as well. So if we think about the products of powers that we did in the first section, or the first set of examples in this video, we have Pythagorean identities for secant squareds, tangent squareds, cotangent squareds, cosecant squareds. So that means we can apply those cases in a similar way.